Well, welcome to my session, everybody. Today we're going to be looking at concurrency in C++20 and beyond. So, obviously, the natural start for such a thing is the new concurrency features that we have in C++20, and then I'm going to talk to you about some of the concurrency features which have been proposed for future standards. So what do we have in C++20? Well, fundamentally, C++20 is a huge release. There's all sorts of extra features added to the language and library. Obviously, far too many to cover today, because that's not the topic. What we're looking at specifically is the concurrency facilities. And so there are fundamentally 5 areas that we can divide those up into. We've got, start with support for cooperative cancellation, so that you can say to another thread, by the way, can you stop what you're doing because we're done for some reason? And then the other thread can then say, have I got a message to check, am I supposed to be stopping what I'm doing? And if so, then it can stop. But this is cooperative. If it's busy doing something that's really important for it, then it doesn't have to stop right this second. It can wait until it's at a suitable point. Related to that, we have a new thread class, Jthread, that automatically joins in the destructor. This is a common source of pain for programmers, is that standard thread, when you have to remember to explicitly join or detach, and if you destroy one without having done so, then your program terminates. So we have a new version, a Jthread, which addresses that failing. We've got some new synchronization facilities, latches and barriers and semaphores, things that can be quite useful building blocks for larger scale features when you're writing your code. And then the low-level atomic library has been updated as well. We can now do low-level weights. You can use atomic ref to perform atomic operations on things that weren't originally declared as atomic. And then, of course, coroutines. Now, I'm sticking them in there as a concurrency facility because they can be used for that, even though they can be used for all sorts of things. A generator is not a concurrency facility, but it's an important use of coroutines. But they can be used for concurrent task and scheduling. So we'll start by talking about cooperative cancellation. Now, it's a common thing. You're using an application, you've got a GUI, you do something, you realize actually this is taking longer than I intended. So I'm going to click cancel and I expect the operation to stop. And you need to, in the code, you need to have some way of doing that. You click download, it tells you, oh, by the way, this is going to take 3 days. You click cancel, you want it to actually stop doing the download and not just, say, well, you click cancel, I'm not going to do anything about it. So you want to have some form of interrupting operations, but it's not just GUIs that have that desire. Any application where there might be something happening that you need to finish. Sometimes if you're doing you're doing concurrent operations and you might have one possible way of using the concurrency available in your hardware is to launch multiple attempts at solving a problem with different techniques. And then as soon as one of them completes, then you say, okay, we're done. Or yeah, you might be doing a parallel find. And so you have different threads that, well, this first thread is going to search this chunk of data, the second thread is going to search this chunk of data, third thread this other chunk. As soon as one of them finds the thing that you're looking for, then you want to cancel the others. So you don't need a GUI, but obviously a GUI is a very concrete case. And in the general case, forcibly stopping a thread is undesirable. You can use terminate thread from the Windows API. You can use pthread cancel to interrupt a thread. But these are quite brute force ones. Terminate thread is very brute force. Pthread cancel somewhat less so, but in that you can register cleanup functions, but it's still a very coarse-grained, high-power weapon to use when actually you want to be able to give your threads an opportunity to tidy up nicely and in a way that interacts nicely with the rest of C++. So we need a way of doing that. C++20 provides us a mechanism for this. We have stop source, which is a thing that you use to say, I want to stop my operations, and the stop token, which is something you can check to see whether somebody has asked you to stop your operations. But as I said before, these are purely cooperative. They have no immediate hard and fast automatic effect. If the task you wish to cancel doesn't check its stop token, it doesn't do anything. So the way of using it is quite straightforward. You create your stop source, you get a stop token, you pass that stop token around to something that you wish to cancel, and then when you want to stop the operation, you call request stop on your source. And then periodically in some user-determined pattern, then you check stop requested on my token. And then presumably you're actually going to stop the task if stopping has been requested. I mean, theoretically, you could say, stop being requested? Yes, okay, I'll print a message that says, you requested stop, and then I'll carry on. It's entirely cooperative. You don't have to do anything, but obviously it is a signaling mechanism, and the reason you're putting it in your code is because you're wanting it to do something. So just to reinterface, if you don't check the token, then nothing happens. This is purely cooperative, and it's important to understand that, because if you're coming from things like pthread cancel where it is forced on you, then you don't get that. As a way of making this easier, then we also stop token integrates with condition variable any, so that if you're waiting for something to happen, then you can interrupt a blocking wait. And so if you pass your stop token to a condition variable, a wait on condition variable any, then when stop is requested, that will interrupt that wait. So you don't have to put a timeout and periodically poll, which is something that you might previously have done. You can actually just say stop, and then the wait will be interrupted. Obviously, you then got to check the stop token and say, why was I interrupted? Was the predicate that I was waiting for signaled? If I'd specified a timeout, was that signaled? No, has that elapsed? Or was my stop token triggered? But you can actually deal with that in the code. So it's quite straightforward. You have your condition variable any, you have your stop token, you call something like wait until, you pass in the predicate you're waiting for. In this case, I'm waiting for my queue not to be empty. And then I also pass in my stop token. The return value is true if my predicate was true, and false if my predicate is false. So in this case, it only returns if my predicate is false if the stop token was signaled, in which case then I can, in this case, throw an exception to say my operation was cancelled. If the return value from wait until is true, then my predicate returned true, so I know that there is data in my queue, so I can remove the values and process them. This only works with condition variable any because it needs to integrate tightly into the internal loop, and doing so with standard condition variable requires too much integration to low-level operating system things. Whereas with condition variable any, then we already need to have an extra layer on top because we can deal with any type of lock. And so stop token can then integrate with that higher level layer. If you're doing a blocking operation that isn't just a straightforward condition variable wait, so you're using blocking IO or something like that, then you need a mechanism of interrupting it. And stop callback provides this mechanism. You can register a callback that is invoked by a thread that requests stop on your operation. So this is done, this injects code into the thread requesting the stop. So you need to be careful what you put there for your callback, but it does provide a means of interrupting your operation. So in this example, we've got a file, we're opening a file, we've now got a handle. We're going to read some data. This is going to be a blocking operation. Maybe we're trying to read the entire file in one go and it's a 5 GB file or something like that. So, but we can then register our callback to cancel IO on this file handle. So then when another thread says stop, then it will then call this callback and issue the cancel IO call and interrupt that read data call, which then will return quickly. And then obviously you can then process that later. In this case, it just returns the partially read data, presumably. And then you can then check the stop token to see, well, did I read only partial data because I was requested to stop, or was there some other issue? This is a scoped object. So when the object is destroyed, then it automatically cleans up and the cancel IO will not be called beyond the end of this function. And obviously, and it references the handle, but the handle is destroyed. The handle was created first, so the handle is destroyed after the destruction of our callback. So it all clears up nicely. See, if you have interleaved lifetimes, you need to be careful that your callback doesn't access something that is past the end of its lifetime. And that's obviously a general issue that you always need to take care of. Now, the stop callback itself is actually a class template, but it has deduction guide set, so you don't ever need to specify what the template parameters are. It automatically deduces it from the callback that you provide. Okay. So we've got cooperative cancellation. We also have a new thread class. Now, I mentioned in the beginning that one of the things about thread class is it automatically joins, but it also integrates with our cooperative cancellation mechanism. So it inherently contains a stop source. So when you destroy your Jthread object, then it calls request stop on that contained source before it calls join. Obviously, your thread still needs to actually check this token in order to do anything with it. And so how does it get this token? It's passed into the constructor. Yes, it's passed into the thread function that provided to the constructor of Jthread as the first argument. So here in our function foo, we are constructing a Jthread. We're going to call thread func, and we're explicitly going to pass it a string and the value 42. But in our thread func itself, the first parameter is a stop token. This is the stop token that is managed by the Jthread. Then we get the arguments that we did pass. We can then have a loop. While we haven't been asked to stop, then we're going to do stuff based on the arguments we've been given to this function, of course. In the meantime, our function foo can then be doing its own stuff. And then when it gets to the end, it calls the destructor of Jthread, which then signals that the stop token should request stop, and then it waits for the thread to finish. The thread func will see that the stop token has been, stop has been requested. It will then stop, it will finish, and then foo can then properly return. So this neatly tidies up. This sort of mechanism, the idea was way in the original proposals that Howard Hinton brought for standardization way back in 2008, I think it was. But at the time, the interruption mechanism, as it was then called, we didn't find a way of agreement on how that was actually going to be implemented and how that was going to work and things. And so that got pulled out, and standard thread didn't have this stop, request stop, and then join feature. But we do now have it. So let's see. you can't, there is no mechanism in the library itself to forcibly stop a thread, and you'd be looking at platform-specific APIs if you wish to do that. But if you use Jthread, you do get this cooperative cancellation, and so you need to always observe the stop token in your thread. It's cooperative. There's nothing that's going to force your thread to terminate unless you use platform-specific APIs like terminate thread. And obviously, the whole point of using a cooperative mechanism is to avoid using platform-specific things. So we're trying to avoid doing that. Okay. So we know not only do we have Jthread and stop cooperative cancellation, but we have additional synchronization facilities. As I mentioned in the introduction, these are latches, they are barriers, and there are semaphores. Now, these can then be used to build higher level things in your program. So we'll start with latches. Now, standard latch, it's a single use counter. So it has a count. It is not just the 0 and 1. It actually, you initialize it with a count, and you allow it have threads that say, when my count is 0, I want to know about it. And in some senses, a latch with a 1 count is very much like a stop token in the sense that it latches, it stays signaled. You count down the latch, and then another thread will wait for that latch to hit 0. See, the use is different because what you use it for waiting for something to happen. So typically you would use it with a block. The wait is a blocking operation, whereas stop token is purely a polling operation because you're wanting to do something else. Latch is used when you're waiting for something to happen before you can continue. And so you might set it for a multiple, a larger count. As long as it's non-zero, then you can create a latch, and then you can decrease things. So you might have, if you're waiting for 5 things to happen before you can continue, possibly because you've got 5 different threads, each of them doing their one thing. Then you set your latch to 5. As each thread does its operation, it signals the latch. When the latch reads 0, then any threads that are waiting will be woken. It's called latch because it latches, like in the electronics item, then its value changes from unsignaled to signaled, and it stays there. It latches in the permanent signal state. And so if after the count has reached 0, if another thread calls wait, then that thread is immediately woken because the latch has already been signaled. So let's look at some code, waiting for background tasks, for example. We have some thread count for some number of background threads, and we create our latch based on that thread count. We then create a certain number of threads to do operations. Every time a thread does its operation, it has 2 parts. We have generate some data, and then we can do some more things. And in this case, then because each thread has more stuff to do, then if you just waited for all the threads to finish, then you wouldn't be able to process your data as early as you might otherwise do. So we have our make data part. We then count down the latch to say, well, I've done creating my data, and then we can do, but I'm going to do more stuff now. So the main thread that called foo, it waits for each of the 5 threads, or however many, whatever our thread count was, to get as far as their countdown. They've all generated their data. And as long as their do more stuff part doesn't access that data, then processing data below is then safe to do so. It can then access the entirety of the data array, knowing that it is safe. This is a proper synchronization mechanism, just as if you had used a mutex condition variable to protect the data. As a very simple implementation of a latch, you could have a count and a mutex and a condition variable, and wait would just do a wait on your condition variable, waiting for the count to be 0, and then each thread would then lock the mutex, decrease the count, and notify the condition variable if the count was now 0. So that would be a very simple implementation. The reason that we have it in the library is because potentially standard library implementers can do something that's actually better on their platform than that. They might have a platform-specific API that already provides this. There might be CPU instructions that provide something similar that you can then use. So by putting it in the library, it makes it a simpler thing overall. We only have the operations that we wish to do and not having to write our own stuff. One thing that I find is particularly useful is when writing multi-threaded tests, because it allows you to have a point in the test threads where they all wait until everything's ready. So you can set up your test data and create a latch, and then you can create your threads. And normally when you create a thread, then there is, it takes time. There might be queuing, they're not necessarily ready. So if you create 5 threads sequentially, then you might find that the first one has done quite a lot of operation before the 5th one has even been created. So if you use a latch like this, then the first thing each thread can do is wait on the latch. And you can use this combined operation arrive and wait, which says, this is one of the signals that the latch is waiting for, and then I'm going to wait for all the other things. So if you have 5 test threads and you set your latch count to 5, each of them arrive at, run their arrive and wait operation. They count down the count, so it goes 5 to 4 to 3 to 2 to 1 to 0. And as soon as it hits 0, all 5 threads then can resume. Obviously, they might not resume immediately because of OS scheduling, but that's the closest that you can get to organizing your, all the threads in a particular known state ready to run your test code. So that if you're testing, for example, what happens to my concurrent data structure when multiple threads access it simultaneously, then everything is now ready to go to access your data structure. Whereas, as I said before, if you start things sequentially, then as each thread starts, then it can do its operations on the data structure. And the first one might have done quite a lot of operations before the last one's even been created. By putting a latch in there, then that gives you, that scope to get everything set up as best you can in the right scenarios. So I think that is something that I use a lot, is latch for waiting for everything to be ready so that then your threads can run the tests. So our next synchronization thing is barriers. Now, barriers are reusable, whereas a latch, once it is signaled, it stays signaled. A barrier resets. So we have this idea of phases. We construct our barrier with a non-zero count, and we specify a completion function to run, which I'll talk about in a minute. So then, as threads arrive at the barrier, then the count goes down until it hits 0. The threads wait for the barrier to hit 0, to be signaled because the count has hit 0. When the count hits 0, the barrier is signaled. Our completion function is called, and then the count is reset after all the threads have been woken. And then we can loop round, and again, threads start arriving at the barrier. So the count was initially 5, the threads arrive, it goes 4, 3, 2, 1, hit 0. We run our completion function, it resets to 5, threads can start arriving back at the barrier again. And then they will wait until all 5 threads have again arrived back at the barrier. But it's a continuous looping scenario. So they're used for looping. They're great, therefore, for loop synchronization between parallel tasks. I've got a repeated operation, which I just do. I can farm out the parts of that operation to multiple threads. When they've all completed, then I can process that chunk and move back onto the next operation. So you read some data, you now process it in memory across multiple threads. You then When it's all done, your completion function then says, okay, this is what I want to do. I've got my data. It's now finalized. I'm going to write it out to a file. I'm going to pass it down a pipeline to something else. Then I can read the next chunk of data, ready to process. Then I can start my loop again, and then all the threads again, they carry on. So once the completion function is finished, the threads can then continue processing. And again, go back around the loop ready to arrive at the barrier again when they've each done their individual chunk. So have a look in code. Now, barrier is a template because it needs this completion function. Now, what we're going to do with our completion function. So in this case, we're going to finish our task. So each thread, it sits in a loop while we haven't been interrupted. We're going to do some stuff related to our worker number. We're going to arrive at the barrier to say we've done our bit. Then when the barrier gets signaled, we loop round again. And if we haven't been asked to stop, then we keep going. Around. And then every time, when the last thread gets to arrive and wait, we call our finish task function before all the threads are released and ready to go around again. So semaphores are the final of the new synchronization things. A semaphore fundamentally represents a number of available slots. You can acquire a slot, and then the count decreases, and then you can release a slot, and the count increases. Obviously, if you attempt to acquire a slot when the count is 0, you can't do that. So either you block, because you just said, I definitely want to acquire it, or you said, no, or if you say try acquire, then it will fail. And the key thing about semaphores that distinguish them from lots of the other synchronization mechanisms is that, particularly relating to a mutex, is that threads can release slots without being the same thread that acquired them. So there's no direct relation between threads that release slots and threads that acquire them. Now, this makes semaphores really, really powerful in general, and also a big potential source of bugs if you get them wrong. But they can then be used to build just about everything. You can build a mutex with a semaphore. You can build a condition variable with enough semaphores. You can build general events with semaphores. You can do them for just about anything. There is not ever so much in the way these are implemented that requires new C++ 20 specific language features. If you've got a C++ 17 compiler, then your library could do it. The thing that is going to mostly, that you couldn't use a C++ 11 compiler for, is the deduction guides for stop callback, because they're quite involved, and the omission of the template parameter means that you need a newer compiler, but it doesn't need to be C++ 20. You can do that with a C++ 17 compiler, and in practice I do, and it works. But yes, so that's the only specific language thing. Obviously, these are highly related and tied in to your standard library and possibly the platform, and possibly when I get on to looking at the changes to atomics, then atomics do tend to require tight integration with the compiler. They don't require C++ 20 language features. They require integration with the specific compiler it's running on, which it might otherwise be C++ 17, but it needs to know what the appropriate compiler intrinsics are. So back to semaphores. Now, semaphores, incredible, powerful thing. If you're thinking about using semaphores, then I recommend there's a book, a free download on the internet called The Little Book of Semaphores. The word little in the title is, I guess it's being a joke. It is not small. It's a couple of 100 pages. And it shows you how to build just about everything with semaphores, things you wouldn't ever have dreamed of doing with semaphores, but you can. And it shows really powerful, complicated things you can do and how you can make a big mess doing so if you're not careful. But if you're actually wanting to use Semaphores, I recommend you look at that. Because as I say, they can be used to build just about everything. You can build latches, barriers, mutexes, condition variables, all these things with Semaphores. I wouldn't recommend you try if you've got them available in the library, but you can. Yes, so there's another question. Can you check stop token while waiting on a barrier? And the answer is no, that is one thing that you can't do. What you could, of course, do is you could register a stop callback, which would trigger the barrier when request was stopped. But there isn't anything directly in the library that allows you to do that. So yeah, so with semaphores, we have this binary semaphore. It has two states, as either one slot free or no slots free, binary. It can therefore, in essence, it is the same as a mutex. The only difference is that whereas a mutex is undefined behavior, if you try and unlock it from a thread that didn't lock it, the semaphore doesn't have that direct relation. There is no direct requirement that the thread that acquired it and the thread that released it be one and the same. But because binary semaphores are a thing, then whereas we have our counting semaphore with a maximum count as a general thing, standard binary semaphore is a special alias for standard counting semaphore with 1 as the maximum count. And it is permitted but not required that is therefore a specialization with a slightly different implementation. As I mentioned already, then you can block with acquire, but there's also try acquire, and then there's acquire for and try acquire until, which have timeouts on them. No, and so the question is, can we wake up one waiting thread instead of all when a lateral barrier hits 0? And the answer is no. If you have a lateral barrier, it by definition wakes up everything that's waiting. Latches, they wake up everything now and forevermore. If you ever try and wait on a latch that's already signaled that you wake up immediately. With a barrier, then it wakes up the specific set of threads that are waiting. And I didn't mention with barriers that the threads that wait have to be the threads that arrive. You can only count down if you are one of the threads involved. You can count down and wait, or you can count down and leave and say, well, I'm waiting. I'm counting down now because other things are waiting for me, but I'm no longer going to wait. So that actually decreases permanently the count. So you can't wake just one thread. You wake the whole set that's waiting. You see, semaphores don't. If you need something that waits just one thread, then have a semaphore, because when you release a semaphore, that releases just the one thread that would be otherwise be blocked trying to acquire it. Because if it was currently 1 and currently 0 and you release it, then it would go to count will go back up to 1. Then somebody acquires it, it goes back to 0, nobody else can acquire it, and so forth. So you could use semaphores for that if you were trying to wait just one thread. I say semaphores can be used for just about everything. It might be complicated though. So how does it look on code? We have a counting semaphore, maximum of 5. We've initialized it with 5. You could initialize it with any count up to the max. We could say start at 0, but in this case it starts at 5. In our function, we acquire it, do some stuff, release it. It's like a mutex, but at most 5 threads can be there instead of at most 1. So if you do something more complicated, then it doesn't end up with a nice little piece of code on a slide. That is what it looks in the simplest case. Okay. Next thing I said was that there are some updates for atomics. We have 3 updates really. Low-level weighting for atomics, one thing. Atomic smart pointers. See, that's quite an involved thing and somewhat surprising if you didn't really think about it, because normally standard atomic, the template parameter that's stored must be a simple, trivially copyable type, and smart pointers are definitely not trivially copyable. That's pretty much their whole reason of existence, is that they do something when you copy them. And so making them atomic is somewhat tricky. And then, of course, we have atomic ref, which allows you to use atomic operations on something that wasn't initially declared atomic. So our low-level weighting, it's very much like in condition variable. You can wait, which waits for the value to change. You give it the old value and it tells you that, and when it wakes up, then you know that it has changed from that value. It might have changed back again, but you know that it did change. And then you've got notify one and notify all, which wait one or all the threads blocked in the wait. So if you call wait, you might not wake up until somebody calls a notify function. So you might get spurious waits, just the same as you do with condition variables. So you need to check what the state of the world when you wake up. Is it what I'm expecting? Is it what I'm waiting for? If it's not, then you can go back, loop round and go back to sleep. Again, this is a low-level thing. It is not something that you can interrupt with a stop token. So you would need to build a higher level structure. But if you're doing weights on atomics, you're writing really low-level code anyway. This is generally, if you're writing you're trying to write a lot-free algorithm, but you need to wait. You've got a lot-free queue, and you're waiting for somebody to actually push an element into it. So there's multiple ways this could be implemented. The simplest, obviously, would be that the library does a spin wait. As I say about condition variables, a condition variable is an optimization over a spin loop. And similarly, a atomic wait is trying to be a library provided optimization over a spin loop. And so, yes, they might spuriously wake up. They don't spuriously wake up if it is a spin loop, but typically the reason that it's a library function is because it won't be. On Linux, it will probably be a call to a futex operation. On Windows, something like wait on address. These are kernel level calls that only wake up when either something has actually, the thing that's been waiting for has actually changed, or there is something like a signal that gets, that the kernel has to process, that then it says, oh, well, I was having to process the signal, so I couldn't check this thing to see whether it happened, so I'll wake you up anyway in case it did. So that's why we get the spurious waits. But we do have these low-level kernel calls which you expect your library to use, and that obviously is what they're there for. So generally, you could not write this faster yourself. If you actually need to wait, then you need to wait. Then there will be some cost to it. It's going to actually have to make that kernel call and check the values, but it's not going to be any more than it would otherwise cost you. It doesn't impact the other operations on atomics. So if you don't use wait, it doesn't change anything at all. If you do use wait, it will be the most optimal thing that your standard library implementer knows how to do on this platform. So unless you know better about the platform than your standard library implementer, there won't be a better way of doing it. With atomic smart pointers, then we now have atomic a shared pointer T and atomic a weak pointer T. Now, it's only those things, nothing else. You are still not allowed to specialize atomic for your own things. You can't pass anything else that's not trivially copyable, only these things. But they are important, and they provide good use for concurrent algorithms, and they already do thread safe reference counting on their own, but this allows you to change a given object atomically. Now, of course, it may or may not be lock-free. Lock-free reference counting things are possible, but they are much more expensive in the normal case. And so it's only if you need the specific properties that you get from it being lock-free that you want it. But if it is lock-free, then it can simplify your lock-free algorithms. You can use just an atomic shared pointer, and rather than trying to do your own memory management sort of code. So that's very important. But even if they're not lock-free, then it is probably a better replacement for shared pointer of T and the mutex, because the library can use something that is specially focused on just this, and it knows that the operation is going to be short because changing a shared pointer is a really quick operation. So it might use a spin lock rather than a generic mutex, and it will typically be better. So certainly, if you are using the C++ 11 standard atomic load, here's my shared pointer, and standard atomic write, atomic store on my shared pointer, then it is definitely improvement over that. The advantage, of course, is that you can't access this shared pointer instance without the synchronization properties. So if you use the shared pointer with a mutex, you could not lock the mutex and try and access the shared pointer, which would in most cases then likely be undefined behavior due to data races. Whereas if you have an atomic of shared pointer, then that avoids that issue. Like all the atomics, then it will have an is lock-free member and an is always lock-free member as well, which are likely to be the same. But in general things with atomic, then they might not be, because it might be that you're compiling for a given platform, and you know that in general this platform may or may not have the atomic operations you need, but it's done at a program startup it determines, and so is lock-free will tell you what it actually is the case, whereas is always lock-free is a compile time constant concept express, and would therefore be false if it was a runtime evaluation, but true if it was always the case. So somebody says, is atomic weight more efficient than condition variable? And the answer is probably yes, because you don't need to lock the mutex. The OS kernel level call is likely the same, but there's no mutex, so you don't have that possibility of the 3 kernel level calls of lock the mutex, wait on the condition variable, unlock the mutex, relock the mutex, and things. It's just the raw kernel level wait. So it is likely more efficient than the condition variable. You use this for low-level operations, not for anything high level. If you already have a mutex, you might as well use it with your condition variable if it's already protecting your data. You would only use the atomic when the entirety of the data that you're accessing is the number of that variable, or something similarly low level. So how would we use it? Well, for example, we're trying to write a lock-free stack. So we have our set of nodes, and each node is going to have a value that it's holding and then a pointer to the next node. We can use shared pointer to the next node and an atomic shared pointer as a head, and then it just is a lock-free stack. Boom, if your atomic shared pointer is lock-free. Then you push on the stack, you create a new node, you load the value, and then you do an compare exchange on head to replace the node with your new node. And then obviously that loops until it succeeds. It's just a compare exchange weak, just the same as you would with any other atomic variable. And then likewise on pop, you load the old head value, you try and do compare exchange strong. If it succeeds, then you did get the value and you can return the value that you popped. Otherwise, then you didn't get it, so you can loop round again. And if the head was null, then your stack was empty. So in this case, within a throw, you could, of course, use the atomic weight operations because they apply to atomic shared pointer as well to do a blocking pop instead of a throwing on stack empty. And if your atomic shared pointer is lock-free, this whole thing is now lock-free. You have a lock-free stack. Boom. If it is not lock-free, then you're probably better off using a mutex around a normal stack. In fact, you might be better off with a mutex on a normal stack, even if it was lock-free, unless you were wanting the lock-free properties. Because a lock-free algorithm on shared pointers is expensive. The normal access is slower than a plain shared pointer, and slower than an uncontended lock mutex read shared pointer unlock mutex. The benefits are that it works in a lock-free fashion with that contention, and therefore provides you, some guarantees about maximum wait times and things like that, and progress, which you don't get from, if you've got a mutex with a blocking lock, then you have no progress guarantees, whereas a lock-free implementation would hopefully provide you some level of progress guarantees. So it's not something to be reached for just willy-nilly, but it is a tool that is there in the toolbox should you need it. Okay, atomic ref is the last thing in these low-level atomic updates, and it allows you to perform atomic operations on things that were not declared atomic. So if you've got a plain int, you can say, well, I want to do atomic operations on that, so I'll create an atomic ref int that refers to my ordinary int. So this can be important if you've got something where you're reading a struct over a network, so you've got a fixed format, but you need to access the individual things with with atomic operations, or when you're sharing your headers with C code, or any other reason why you have a fixed binary layout that you can't put standard atomic int in there. So, but you do want atomic operations. But the important thing to remember is that whilst you have any standard atomic ref objects that refer to a given non-atomic value, all accesses to that variable must use the atomic ref. You can have multiple atomic ref objects that refer to the same object, and that's okay. But you can't have standard atomic ref referring to my int and then just access the raw int with another thread. That is a data race. That is undefined behavior. Everything will potentially go wrong. Don't do that. So somebody says, do lock-free synchronization primitives always perform better on mutexes? Can you provide an example where this is not the case? So no, they do not always perform better than mutexes. In an uncontended case, the locking a mutex and then having a simple data structure is probably faster than having a lock-free data structure that's equivalent. If you've got a lock-free hash map, is really complicated. A lock-free stack isn't epically simple. If you've got low contention, then the mutex lock is going to be really quick. It's probably just a single atomic operation. Then you have some non-atomic accesses to your simple data structure, and then you have a mutex unlock, which again is probably just a simple atomic store if you've got a uncontended access case. A lock-free data structure that's the same, on the other hand, is just all atomic operations and is probably more complicated because it needs to deal with the potential interleaving of operations. Because whereas your a simple hash map can say, oh, well, no, I've got too many values, fine, I'll redo the number, create new buckets and reallocate things between the buckets. If it's a lock-free one, then if you're trying to reallocate things between buckets, somebody else on another thread might be accessing your data structure at the same time. So you've got to do something complicated about making sure that everything still remains synchronized correctly. That makes the actual algorithm itself really complicated compared to the single-threaded case. And so in an uncontended case, you've just got a load of complication for no gain compared to the mutex. Whereas if you have a highly contended thing where suddenly the lock-free properties are important because you want multiple threads to be able to access your hash map without having to wait for the other threads to finish, without that blocking that the mutex would force on you, then the lock-free provides you some benefit and potentially improves your overall performance. But it's never, you should never reach for lock-free stuff as the first tool in your toolbox. It should always be, I really need this for some specific property. And then again, profile and hope that the added complexity actually gained you some benefit. Because if it didn't, then switch back to a mutex and a single-threaded data structure, because that is overall simpler and easier to maintain. Okay, so how would we use atomic ref? Well, we have a simple C structure. It contains only simple data types. Then we have an integer, and we want to perform atomic operations on that integer, like increasing the count. So we create an atomic ref that refers to our object, refers to the integer. Then we can do an increment, and that just increments the value atomically. Okay. So coroutines are what's up next. But there is a question about atomic ref. All accesses must use atomic ref if I have a chunky execute only in one thread. So yes, if you only have one thread, if you create your atomic ref at the beginning, then your atomic ref is now alive. And so if you then do a load of non-atomic stuff in the middle and then try and do an atomic thing at the end, then all that stuff in the middle is potentially unsafe. And so you need to avoid doing that, because in the general case, then your atomic ref might actually create a new copy of the variable in some, or flag that memory location in some special way, so that the accesses are through the ref perform different operations than a straightforward write. And then if you then perform the atomic ref operation later, then now the data structure is not in the state that it thought it was. And so that then is undefined behavior. As with undefined behavior in all cases, it might perform what you expected it to do in the scenario where you test it. But that doesn't mean that it's safe code and you can rely on that being the case. Certainly, if you're trying to be portable, then you don't want to do anything that is technically undefined behavior, because the behavior will vary between platforms. So you need, if you're using atomic ref, you need to use always atomic ref. You can reduce the synchronization overhead of that by making the memory accesses relaxed if you don't care about the ordering. And then on common CPU architectures like x86, a relaxed read or write is exactly the same CPU instruction as a non-atomic read or write. So there is that benefit there. You avoid the costs if you don't actually need them. Okay, so let's move on to coroutines. Coroutine is a function that can be suspended mid-execution and then resume later. And when you resume it, then it continues from the suspension point. And all the local variables have exactly the same values because they were saved. It was stopped mid-execution. But how that relates to the rest of the code varies. C++ 20 provides stackless coroutines, so it's only the local variables of that function that are preserved, not the whole call stack. Which means everything is localized. Memory allocation is minimal because if you have a stack full coroutine and you save the whole call stack, then when you switch it, you've got to have a whole new call stack. Whereas if you've only got the local variables, then you don't need that. You only need whatever you've got locally, which is generally not vast amounts of data. So we have minimal memory allocation and therefore the potential for millions of in-flight coroutines. You're not going to be able to have millions of in-flight coroutines if you've got a whole stack saved, because suddenly you end up with gigabytes of stack data because they quickly accumulate. And it also means that there's a benefit because it only needs to look at the current context, which means that it's all there. And therefore, in lots of cases, in particularly simple single-threaded cases like generators, the whole coroutine overhead completely goes away. And so Gor Nisharov, who wrote the compiler implementations for this for Clang and Visual Studio, he calls it the disappearing coroutines, because you write it in your code, but when you look at the assembly language, there's no coroutine stuff there at all. We've got a generator that generates some ints. You look at the generated code, and you've just got a series of ints appearing. And so it does have optimization properties, but the lack of saved stack can then make some things more tricky or unexpected. So there are proposals for stackful coroutines as well, but they're not in C++ 20. So in theory, you can then use coroutines with things like futures. So we can have our future for remote data. We can call so we have async get data that returns that. We can co-await on that. It gets the data. We can then process that and then return value. So we have two coroutines. So we have a coroutine here that retrieves a value from some async source. And then if you've got a coroutine that waits for the data from retrieved data, then it will work. So potentially, this is how you would use coroutines to work with concurrency, because when you hit that co-await in the retrieved data coroutine there, then it will suspend your task, tell the scheduler that I'm waiting for my coroutine, and therefore you can run something else. And then when the data becomes ready, then it will resume this coroutine with the data, and everything, all the local variables are intact and the state is ready. But that requires more than we get from C++ 20, because C++ 20 provides the mechanics but doesn't provide the library facilities. We have no library for support for coroutines, which means you need to either write your own support code, which in the concurrent scheduling case is hard, or use a third-party library. So you might like to look at Lewis Baker's CPP Coro library that provides lots of things like tasks and mutexes and stuff that work with coroutines. So hopefully we're going to get something in C++ 23 or later that actually deals with this. We will have some form of coroutine support library beyond the mere mechanical compiler hooks, which is all we have at the moment. Okay, so what we have in the new standard, so that's what we have in C++ 20. What about future standards? What can we hope for? So there's lots of proposals. Some that I'm going to mention today, we've got synchronization wrapper for ordinary objects. So you don't, if you just want an int that's protected by a mutex, you don't need to have an int and a mutex and then worry about, oh, have I got the mutex locked? If I got the right mutex locked, things like that. You just wrap it all together. Like you might use standard atomic, but if your object is more complex, say it's a string or a vector, then you couldn't use that with standard atomic. You can use a synchronization wrapper to make that easier. There's proposals for enhancement to standard future, make it better, more usable for proper task manipulation things. There's obviously the much awaited executors library. Like I just said a minute ago, we're looking for coroutine library support for concurrency. There's proposals for concurrent data structures and then safe memory reclamation facilities, which would then be helpful with implementing those concurrent data structures. So, synchronization wrapper, synchronized value. Fundamentally, as a concept, encapsulates a mutex and a value, so you can't access the value without locking the mutex. And it's easy to lock a mutex for a whole operation rather than just a single member function calls. Also, if you've got an operation involving multiple values, then you can lock the mutex for the whole of the operation across all the values, and it makes sure all the mutexes are locked and you don't have to worry about deadlock due to getting things locked in different orders. So if you had a synchronized value of a string, for example, then you can get the value. The way you access it is you apply a function, like if it was a tuple. So you apply it, and it's a bit like visit on variants as well. You pass in the function and then the synchronized value you wish to apply it to. And so then in the function, when it's running, then you've got the non-atomic, non-protected raw value that you can access. So you can easily, you can just return the value, or you can append the string by accessing in there, and it locks the mutex, calls your function, then unlocks the mutex conceptually. See, there's no guarantee what form that synchronization takes, whether it's a standard mutex internally, whether it's a spin lock, whether it's a lock shard in the library or something else, but the library just takes care of it. You can then do an operation across two things, so you can concatenate two strings together by applying a function that takes two values, and then you pass it to synchronized value objects, lock both the mutex, call your function, unlock the mutexes. You don't have to worry about deadlock or anything like that. So enhancements to futures. So the Concurrency TS, which has now been out for a good few years, does provide potential enhancements. So continuations is the big thing, which I think is probably the most important aspect. It allows you to say, when this feature is ready, then I want to do another task, and I'll get a future back for the result of that task. Alternatively, you might want to wait for all of a set of features. I've spawned a load of tasks, so when they're all ready, then I want to do something. Or when the first one is ready, I want to do something. Now, you see, this is a TS, so it's standard experimental namespace. That doesn't mean that if you've got a compiler, if you've got an implementation, it doesn't mean that the library is poor quality. It means that the interface is non-standard and may change before it becomes properly member of the standard namespace. So these are TS. There's not many implementations around. My library provides it. I think Stella's HPX provides it, but I don't think any of the standard library implementations actually ship it or even have plans to at the moment, which is a shame. But it's there as a TS, so I hope that we will see more implementations at some point soon. So the idea of a continuation is it's a new task to run when your future is ready. Way we chain these is just like in other things, like JavaScript. You call then and you provide a new function, and then you get back a new feature. The source feature is no longer valid because standard feature is a one-shot thing. So If you've retrieved the value, you can't retrieve it again. In this case, you've said, well, I'm going to retrieve the value and pass it to my function. So that's all happens internally. And so the original is then no longer valid. As a consequence, only one continuation can be added to a given future. Though obviously now you've got a new future, so you can then chain new continuation on the end of that. So we have to try and find the answer, and then we want to process the result when we've got it. So we can then call f.then to chain the two together. And this schedules the task in some unspecified manner. So this is one of the things why it's in a TS. We're wanting to provide the implementers to say, well, how is it best to schedule these tasks? And to be quite honest, the answer is going to be executors, which we'll cover in a minute. But for now, then with the concurrency TS, it's not specified. It will run that result, the chain continuation in some unspecified thread. You can also use continuations with shared future, because shared futures allow you to access multiple times. Then the source remains valid, and you can chain multiple continuations on the same object. And then the continuation function must also take a shared future so that it knows that it's sharing the object with other things. But other than that, then they work exactly the same as with futures. So when any gets us a new future that is ready when all the ones you provide it are ready. So if you've got speculative tasks, or you're doing a find and you want, as soon as the first one arrives, then you want your result to be ready, then you can use when any for that. Because what you get back is a future, you can then chain a continuation. So you say, when any of my futures are ready, then do the processing. And obviously you could then use stop tokens if you were doing it for speculative tasks or something like find. Your processing could first trigger the stop token, say all the rest of you give up, and then I'm going to process the results. So you look at this, you spawn your async function, you spawn your other async function, you move those futures into when any, you've then got a new future which you can then chain a continuation on, and then you can finally do something with the final result of that continuation. When all is the companion. It waits for all the futures in the set to be ready. So if you've got a load of subtasks and you need them all to be finished. So whereas like with, so very similar to the way you might use a latch, you have all your tasks, and then when each one counts down the latch, in this case, each one returns a future, and then you say when all, and obviously that makes it more composable because you don't need to care about the, whereas with the latch, the function that's doing the task needs to know that it's got to signal the latch. If you use futures and when all, then the task doesn't need to know, it just knows it's returning a future. And so again, we can do that. We can spawn our tasks. We can move them into a when all call. The results we can then chain a continuation. Okay, so executors. Executors are one of the most awaited things from concurrency in C++, and they were not ready for C++ 20. Hopefully, they will be ready for C++ 23. Fundamentally, an executor is an object that controls how, where, and when a task is executed. For example, a thread pool. A thread pool is an executor. It runs tasks. It chooses which thread they run on. At the fundamental level, they're really simple. An executor is something you can copy around and check to see whether it's the same thing as something else. And then you can execute something on it. And then the framework builds everything else. So obviously, if you've got a thread pool, the executor is not going to be the thread pool itself. You're going to have some sort of handle to that thread pool. But fundamentally, that's what you get. And then you've got the task, so you can call the basic level. You can call execute of an executor and give it a task to run, and it will then choose how and when and where to run your task. You see, you can hope that you've got some decision making why you've chosen that executor. If you need something specific from it, then you can use standard require to ask for a property. This is one of the things that is currently up for debate about how we're going to do this. But if you want to guarantee that that your executor is going to always run your task somewhere else, so we're not going to block waiting for it, then you say, I want to require that my executor is never blocking. And then you've got a new executor that won't ever block. And obviously it will, and the idea is that will fail to compile if your executor doesn't provide you that choice. If you can't get that property, then it won't compile. Whereas, and the reason you might do that is because some executors, for example, will choose to run your task on the current thread if the background threads are busy, or it feels like it's a good plan for some other reason. Whereas by saying I want to require that it's never blocking, then you know that it won't run it now. It will post it on the internal queue to run at some point. So I said, thread pool example, the current paper provides us with a static thread pool, and you start your pool with a number of threads. You then get the executor for that pool, and then you can run some tasks on that pool. So that's all been straightforward. Then there's an extra level of flexibility and complexity, sadly, because they go together, that is then provided in the executor's paper. This is the idea of senders and receivers. So it allows you to split things apart. So a sender is, well, some initial work that you might to do, which might be nothing, and then binds in the executor that work is going to be done on. And then you have a receiver that accepts the result of the first bit of work and then does some more work on that executor. It might then pass work to subsequent executors and create a chain, but it might just store the result. But it's by splitting things into two parts, then it allows more flexibility and allows you to build more complex things. So this can actually be used for building a then function for doing continuations and things like that. So it can work well with the ideas for features that were introduced with the Concurrency TS. So a sender just, the receiver provides 3 contexts. Then you need set a value, which is when your sender has a value to give you, set an error because something went wrong, or set done to say, well, I don't have a value or an error because I stopped. And so then you'll send, when everything is running on the schedule on the executor, then your sender will call one of these 3 values on the receiver. So then you can do the processing. The simplest thing to do is you call submit, and you give it a sender and receiver, and it ties them together. The executor is encapsulated in that sender, and so then that actually runs the 2 on the executor. You can split that apart if you wish, if you want to tie them together but not run them yet. So you can connect your sender and your receiver and then start that operation later. So yeah, if you've got a task and you tie it in, and then you don't want to schedule it yet, then you can use the connect and start as separate operations. If you've got a really simple case, you can just wrap your executor into a sender directly by calling schedule, and that just gives you a sender that encapsulates this executor with no work. And so then the receiver won't have any parameters when set value is called. So our simple receiver has a set value that takes no parameters and just does, and this is where we do our actual work. So this is a way of, like just calling execute on my work, then we create a sender with schedule, then we create a receiver that does the work and tie them together. If you want to have a look at that, then look at libunifx, which is a sample implementation with lots of documentation, including extensions that go beyond what the current paper provides, but can therefore is actually this is implemented by the people working on the paper. So it does relate directly to what the standardized executor model is going to be, even if not everything in the library makes it into the next standard. I'm also hoping that we'll get coroutine support from concurrency. It would really nice to see something like tasks where you create a task, you can wait on a task, wait on another task. These are all coroutines. You can schedule that with an executor, and that will then schedule the subsequent parts of the coroutine when the data becomes ready. And things like CPP Coro provides the basis of this sort of operation. Obviously, it needs to be tied into executors, though the part of the reason for the sender-receiver model is that allows that to work better with coroutines, because you can tie things together. You can encapsulate the executor that your coroutine is going to run on in the sender, and then the receiver can be the coroutine as and can invoke the next part of the coroutine as the data gets processed. So the building blocks are there. I'm hopeful that we will actually get things that work like this at some point soon, but we don't have it in the standard yet. This is why it's in the future standard part of the talk. Concurrent data structures. Well, lots of the, if you're writing concurrent code, if you're doing anything other than embarrassingly parallel stuff, where each thread works on its own data, then you need to share data. And either you need to protect it with simple things like a mutex, you lock your mutex, you access your data structure, you unlock the mutex, or you need a data structure that's designed for concurrent access from multiple threads. There are proposals to standardize some of these. Hash maps and queues are probably the most important data structures and the most widely used data structures for concurrent accesses. Obviously, in a given application, you might have specific data structures which are better and more appropriate for you. But that is the C++ standard doesn't deal with two application-specific things. So someone's saying, have we got plans for higher-level abstraction like actors threading models? There are no concrete proposals for that. Pretty much everyone who's focusing on concurrency models is working on the executor's proposal, and nobody's putting in proposals for actors. Once we've got executors, I imagine that people will say, we need actors too. But for now, we don't have concrete proposals for that. Okay. Queues, core mechanism for communicating between threads. If you're going to have actors, you need queues, because you need to have message queues for passing messages back and forth. The idea is simple, like we have standard queue for anything, you push things on, you plot things out. If you have a concurrent queue, you want to push data on, you want to pop data off, and have it just work regardless of which threads things are, and make that seamless. We have concrete proposals for this. I'm hoping that we will get them standardized at some point soon. Likewise, hash maps also provide a mechanism that is used between multiple threads. We use hash maps ideally because they're fast for lookup. But if you're using mutexes for synchronization and it's a highly contended case, then that can be slow. So if you have something that is mostly static data, then using a standard mutex is really just adding performance overhead, because everything has if you've got 100 threads trying to access your data structure, they're all reading, but because occasionally somebody might write, you need a proper standard mutex rather than just making it constant, declaring it, and have everyone can just access it fine. Then it is better if you have an implementation design for fast concurrent access, but with occasional concurrent writing. And so we have proposals to do those, but again, I hope we get them. If you're going to implement these things yourself, you need to see some method of safe memory reclamation. And particularly if you're looking at lock-free algorithms, if you're trying to delete objects, you need to know nobody else is accessing my object. Doing this with reference counting is tricky and adds lots of things overhead. So there's various ways you can do it. One way is to use something like RCU, which is used extensively in the Linux kernel. This provides a lock-free read side. And then if you're actually trying to delete an object, then you either have to do a blocking object or blocking operation to say, I'm going to block now till there's no readers and it's safe to delete my object, or you defer the deletion to a background thread, which then does the cleanup at a time when there is no readers. Hazard pointers offer an alternative. If you're going to go for the deferred deletion pattern, hazard pointers give you an alternative with a different set of performance trade-offs. And so the hazard pointers track how many threads are referencing a given object, whereas RCU is about how many readers are there currently now and sort of generations and things like that. So that it keeps they have different models of how they track access, and they have different trade-offs, and they are both proposed for future C++ standards. So you can then look at the trade-offs and see which one is most appropriate when you are designing your own concurrent data structures. So I said these are proposals. Here are the concrete paper numbers. If you get the PDF of this, all these are links to the papers. But if you're just watching on the video, then note them down. wg21.link/paper number will take you to the latest version of the paper. You imagine that everyone watching this talk already knows about my book. It's C++ Concurrency in Action. Second edition covers C++ 17, and the Concurrency TS doesn't cover the new C++ 20 stuff, apart from that which is already covered by the Concurrency TS. So latches and barriers are in the TS, atomic shared pointer is in the TS, future extensions are in the TS, so these are all covered, but those stop tokens are not, and semaphores are not, and low-level atomic things like that. Okay, has anybody got any more questions? If you post them in the Q&A, then I will answer them. So yes, if anyone comes up with any more questions, then I'll be following along on the Track A Discord to for the next short while. If anyone wants to ask any further questions.